Professor Oleg Morozov, and he will tell us about extensions of Lie algebras and their relations to integrability of some equations of mathematical physics. Oleg, you're welcome.
Is it possible to hear me? Something. Okay. Well, today I continue a series of talks devoted to the problem of recognizing whether a given PDE is integrable, in sense that it admits a lax representation or a differential covering. In my talk, they will be synonyms, differential coverings and lax representations. Well, in other words, the problem is to find intrinsic conditions, conditions that are invariantly related to our equation that guarantee or at least indicate that equation admits a lax representation. In previous talks, I discussed an approach based on the twisted extensions of the symmetry algebras. Today, some development of this approach, I'll show that these developments allow to find new lax representations for a number of equations from the fluid dynamics, magnetohydrodynamics, dynamical meteorology, and so on. Well, I'll start from the two-dimensional Euler equation in the vorticity form, this equation. Sorry. Here, delta U delta is just Laplacian operator, and the bracket is just the Poisson bracket. Well, this equation is the two-dimensional Euler equation in the vorticity form. This equation describes dynamics, describes evolution of the potential of two-dimensional unviscid incompressible fluid.
1 plus 2.
Sorry?
1 plus 2.
One, no, two means the fluid is two-dimensional. Well, the lax representation for this equation is known. This lax representation sorry. This lax representation was found by Yang-Guan, Charles Lin in this year. Well, let me mention that the parameter lambda in this lax representation is removable. If lambda is not equal to 0, then we can change the variable v, the fiber coordinate, and in the following manner. We replace v by x of lambda v, say tilde. And then we obtain the following system. Sorry. Well, no spectral parameter in this form after this simple change of the variable. I tried to reproduce this result to construct this Lax representation using the approach based on the twisted extensions of the symmetry algebra of our equation. And now I'll discuss what happens when I try. Well, first, it's much easier to deal with equation in hyperbolic forms. In other words, just for simplicity of computations, I make the change of variables. Say tilde minus plus y tilde. Sorry. This change of variables transforms our equation to the following form. Where d of u is just ux, y. Well, and then I'll drop the tildes.
Yes.
Well, this form is just for simplicity of computations. Well, then, in the full, it looks like this. This equation. Well, to apply the approach based on the twisted extensions, first one need to find the symmetry algebra. The symmetry algebra, let this equation be called E. It's symmetry algebra or infinitesimal symmetry algebra. The algebra of contact of infinitesimal contact symmetries of our equation has the following form. There are 5 standing alone symmetries. Let them be called psi 0, psi 1, and so on, psi 4. And this algebra acts on the infinite dimensional ideal generated by some functions psi 1 of A1, psi 2 of A2, psi 3 of A3. Finite dimensional, 5-dimensional algebra acts on big ideal of symmetries. Here, A of I are arbitrary functions of variable t. They are supposed to be smooth. Well, and to proceed, we need to restrict this Lie algebra, this symmetry algebra. We allow these functions to be polynomial. We require them or restrict our considerations to polynomial functions. So now we suppose that our functions are polynomials. Then we take the dual forms to these symmetries. Well, I don't write explicitly these symmetries because this will give nothing.
Well, 3 shifts and 2 gauge.
3 shifts, 1 scaling, and what else?
Not 2.
Sorry, a moment. No. 1 scaling, and the fifth symmetry is quite intricate. Something like this: u plus xy, and some changes in x and y. Well, the explicit formulas can be found in the preprint this prefix. So now we take the dual forms, the forms that are dual to these symmetries. Let them be called alpha. So we have forms alpha 0, alpha 4, and the forms that are dual to symmetries phi I of t in the degree k. And let say the dual forms to these symmetries, let them be called omega ik. Well, these alphas are dual to psi. Well, the structure equations for our Lie algebra can be written in quite short form if we consider the formal series of forms, sum for k from 0 to infinity, h in the degree k factorial, omega ik. Here h is a formal parameter, and the exterior differential of this h is equal to 0. Well, then we find, using, say, the moving frame approach, find the structure equations for our Lie algebra. They have the following form. Actually, okay. The structure equations have the following form. D alpha 1. Sorry. And structure equations for this formal series. Well, we can find these forms, all of these forms, but actually of interest are just the forms alpha. Let me write them explicitly. Somewhere is there. Alpha 0 is dq divided by q for 1 u dt. Alpha 2 d u x y u alpha 3 alpha 3 d u x y y u x y y minus u x y dt alpha 4 d logarithm omega 1 0, the first form in the first series, u x y y divided by q dy plus u x dt omega of 0 u x y y q okay, no space 0 u x y u multiplied by d y dx minus u x dt. This forms. Well,
What is Q?
Q is non-zero parameter. Q is free parameter in this consideration. When we are living on the bundle of the third order jets, Q is a parameter. One can check that invariance of these forms is equivalent to the fact that the diffeomorphism is the symmetry, it belongs to the symmetry pseudogroup of our equation. Well, some prolongation on this Q, but well, let me skip the details. Okay, now we look at these structure equations and say, from these structure equations, it follows that the first cohomology of our Lie algebra, well, after this restriction, the Lie algebra be as GDEq. Well, the first cohomology group of our Lie algebra is generated by alpha 0 and alpha 4. Then we compute the second twisted cohomology group of this Lie algebra. Shall I recall the?
Yes, should we?
Okay. What is? Well, suppose we have a Lie algebra G, and with non-trivial first cohomology. So there is a form alpha from G star such that d alpha is equal to 0. Then we define new differential d, new differential, let it be d c alpha. It applied to a form omega, it is d omega minus c alpha product with omega. D is Ellenberg Chevalier differential, usual differential for Lie algebras. Well, so it is quite easy to check that the square of this operator is 0. It follows from the fact that d alpha is equal to 0. So there appears, we can construct the cohomological complex associated to this differential, and cohomology groups of this differential are referred to as twisted cohomology groups of the Lie algebra G. Well, in our situation, the first cohomology group is two-dimensional, so we take arbitrary closed form form. And it turns out that this cohomology group is a-dimensional. It is generated by 8 twisted cocycles. We are interested just in one of them. This cocycle. 1 plus omega 1 0 omega 2 0. This cocycle corresponds, is associated to C1 equal to -2 and C2 equal to 1. And 7 other cocycles that are of no interest to these considerations. So this means that the following equation, d sigma equal to 1 to alpha 4 minus 2 alpha 0 multiplied by this sigma plus this cycle. This equation is compatible with the structure equations for our Lie algebra. All the forms alpha and omega are omega 1, omega 2, omega 3 are known, so we can find this sigma explicitly. The sigma is one form turns out to be of the following form: uxxy xyy divided by q squared multiplied by dv minus u x plus 1 over 2 y dx minus x dy.
And what is V?
And V is integration constant when we integrate a partial differential equation, and this V is now it's a constant, but then it appears to be the pseudopotential, the fiber variable in the Lax representation. Now, what are we doing now? We consider the linear combination of this sigma with, let it be called tau 1 sigma minus C1 alpha 1 minus C2. This C are not the same as C2 omega 1 2 minus C3 omega. Linear combination of the sigma with horizontal forms. These forms, let me recall. Alpha 1 governs evolution of T. Omega 1 governs evolution of Y, and omega 1 0. Omega 2 0 describes evolution of X. These forms are horizontal, and let them be called basic horizontal forms. So we take linear combination of this sigma with basic horizontal forms, and then analyze what is when we restrict these forms, when we put V to be equal of a function of txy and u function of txy, then this form defines a system of PDEs. Well, it is not so hard to show that C1 can be put equal to 0. We can change variables such that these constants, this is 0, and these constants are 1. And then it turns out that this, well, the Walk-Westerstebrook form found in this way is, or the Walk-Westerstebrook form for the following Lax representation of differential or differential covering for our equation. Plus u minus 1 over 2 E of u delta u commutator with V is equal to 1 over 2 E of delta u, where this u capital is a differential operator, the differential operator of the following form. This E, say of u, is x ux plus y uy. Ux plus y uy. well, the full formulas are written in the preprint. You can, I hope you can believe me that it is so. So this is not the Lux representation found by Lee. In other words, the approach, if we use just a twist extension of our of the symmetry algebra, we find something, some new Lux representation.
But also without
this Lux representation has no parameters at this moment. Well, what shall we do? What shall we do if we want to reproduce Lee's Lux representation? Well, let me discuss the following construction. Construction that is called Lee-Reinhardt transformation algebras. Well, suppose we have an abstract Lie algebra, finite dimensional or with countable basis. And suppose we have a representation of this Lie algebra by vector fields on a finite dimensional manifold or open domain in Rn. So we have a homomorphism from our Lie algebra, this G, to vector fields on, let it written C W capital. W capital is an open subset of Rn with some natural m. Well, let me, for short, denote this algebra, commutative, associative, unital algebra by A. Now, let's consider the following vector space. This A tensor product with G. And define, well, this object is left A module. And a Lie algebra over R. Well, we equipped it with the following map. Maps the Lie algebra to the derivations of our algebra. And then consider the linear space and then equip with this linear space with the following bracket. Okay, this linear space turns out to be a Lie algebra if we equip it with the following Lie bracket. If we require that the Lie bracket there holds the following property.
Why define bracket on this tensor product?
Yes.
And X is an element of tensor product.
X, Y from the Lie algebra, A from A. we require this to hold, and then okay, I can put some b here, and then a multiplied by b minus rho y of b multiplied by tensor with x. This object is called the Lie-Reinhardt transformation algebra associated with our algebra G and its representation rho. In coordinates, if G has the following basis, and the structure constants I xi, the well, let B G be dual forms to this axis. Then the structure equations for this Lie algebra is of the following form. J is less than K. Well, and if the representation rho is defined by some functions, say H, K, I of W, D, W, K, sum for I. Then the structure equations of the transformation Lie-Reinhardt algebra. The structure equations are obtained by appending to this system the following equation: D W K is equal to sum for I. Sorry, for I. Oh, sorry, this is not correct. Sorry. This is for K from 1 to N, this sum. And here sum for I from for all I of H, this H, K, I, W, theta. And this requirement should be 2O. No. W is 0 form. The W is coordinate on this. Well, and this requirement is the same as to require that the differential of the differential is equal to 0 as a consequence of this system and of this system and this system. Well, in particular, when Lie algebra G can be written in the following form: finite dimensional superalgebra X on some perhaps infinite dimensional ideal, and well, dim A is less than infinity. The subalgebra is finite dimensional. If we have a representation of this subalgebra, then we can extend it. We can extend it, consider new representation, which is equal to rho of x when x is element of our algebra, and 0 if x is element of the ideal. To extend to the infinite dimensional ideal by 0. Well, this situation, when we have finite dimensional algebra that is acting on infinite dimensional ideal, is the situation with our symmetry algebra of the two-dimensional Euler equation. Now let's take the following picture. Let's take the subalgebra generated by psi0, and it acts on everything positive. Well, the representation is very simple. It follows from this formula that the representation is U dq. Well, extend this representation by 0 to all other elements. And we obtain the Lie-Reinhardt transformation algebra associated with this subalgebra and this representation. This means that we allow our forms to be multiplied by functions of Q, of this parameter Q. So now we consider another Bohlqvist-Estabrook form. We take our sigma and then arbitrary functions of Q multiplied by the basic horizontal forms. Now these functions are not constant; they're functions of this Q. Okay, then analyze this tau the systems obtained from this tau2, and we find the following. The choice when h1 of Q is equal to 1 and h2 of Q is equal to 1 minus 1 over Q is associated, well, the corresponding Lax representation has the following form. dv is equal to uv, the commutator uv plus u minus 1 over 2 e of u, and nabla u, delta uv is equal to 1 plus 1 over 2 e of u. This one, this one appears actually this one. Well, it is closer to Lie-Lax representation. Well, then let's generalize this construction. Let's consider now the four-dimensional algebra.
But in principle, we could construct an expert for arbitrary choice of H1.
Yes, but if we analyze, we say that nothing prevents us to put this one equal to 1, and then more or less in unique way we find up to some scaling, some transformation, some change of variables. Well, now let's consider another Lie algebra, this Lie algebra, and it acts on psi 3 and all our phis. And again, we know the representation. The representation, again, is given from these explicit formulas. We say, well, the representation is from this Lie algebra to the vector fields on R4 with coordinates W1, W2, W3, W4 that are the same as Q, C, V3, UXY, and UXXY, UXYY. The representation can be extracted from these formulas, and it turns out to be the following. Rho of psi 0 is again now dw w1 dw1. Rho psi 1 is 1 over w1 dw2. Rho psi 2 is w1 dw3, and rho psi 4 is w4 dw4. The representation. What does it mean? It means that we can consider, now we can multiply our Maurer-Cartan forms by functions of all this W1, W. What do you mean?
When you compute the first two vector fields, unknown periods.
Perhaps some misprints, perhaps. Well, let's check. Text. Let's check. No, it seems to be okay. Well, so now we can multiply the Maurer-Cartan forms by functions of all these variables. So we take the Walquist-Estabrook form as the following linear combination: sigma minus H1, G1 of W1, W4, omega 1, 0 minus G2, W1, W4, omega 2, 0. Then we analyze what happens. Well, W are written here.
Yeah.
And then it turns out that if we choose G1 to be equal to the following function, okay, G1 to be 1 plus P of W3 divided by W1, G2 W4 Q of W3 divided by W1, where P and Q are arbitrary functions of their argument, of this argument, then the corresponding Lax representation will be of the following form. Plus U minus 2E of U plus an arbitrary function, this function Q of this, and this is UXY. And now we have the following 1 over 2E of du plus this function of du. This Lax representation. Once again, P and Q capital are arbitrary functions of their arguments. Now, we say the following. This Lax representation admits a non-removable parameter. Namely, we consider two cases. The first one is when G is P of W3 is not equal to a constant multiplied by W3. If so, the symmetry, the scaling of our equation, of the Euler equation, this scaling, this symmetry, does not admit a lift to the asymmetry of this Lax representation. So we take x of say epsilon EGT minus U GU and act on this Lax representation. It turns out that, let me write it here. After this, we obtain the following: lambda Q lambda minus 1 du lambda P lambda minus 1 du. The parameter is non-removable because of this. Well, when P is proportionally is equal to some constant, say gamma multiplied by W3, then the following symmetry, this well, plus cy dy minus x y du, this symmetry with this, well, the fifth symmetry. This symmetry does not admit a lift, so we obtain another Lax representation in this situation. is equal U the commutator plus this plus now what? U of du plus epsilon, and the second equation, sorry, du v is equal to 1 over 2 e of du plus gamma du plus gamma epsilon. And the parameter epsilon, at least here, is non-removable. Yes.
Excuse me, please. If you write the last representation, I guess you should automatically write the differential consequence. I mean,
Differential what?
consequence equation, which follows from last representation.
Yes, it was in the very beginning. Okay. Okay. This equation. Okay. It is just a
Okay.
if we replace this d by delta, it turns out to be the two-dimensional Euler equation in the vorticity form. So, well, okay, let us replace now. Replace. We return, we make the inverse transformation, and we obtain the Lax representations for the initial Euler equation in this form. Just replace d by delta everywhere. Well, if P is not of this form, this Lax representation with the non-removable parameter lambda. Otherwise, this Lax representation.
Do you mean that if P is not of this form, then this complicated symmetry can be lifted?
Any choice of P that is not of this form means that this symmetry can't be lifted.
And the second one, I mean.
Second one, well, this symmetry admits a lift.
Yes.
But this does not. Yes, what? Okay, it's. So we obtain Lax representations. Actually, they depend on functional parameters, one functional parameter here and two functional parameters there, and non-removable parameter lambda. Well, now what about the Lax representation found by Lee? What shall we do to obtain this Lax representation? Sorry? Alternative what?
Ты говоришь, я собираюсь тебе свое написать.
Well, Max, ты опоздал. From the very beginning, there was a Lax representation found by Charles Yang-Wan Lee. I wrote it in the following form because it can be written in this form. So, how to obtain this? The answer, we put what? We put say what moment. Something. We put this function equal to 1 identically, and this function equal to 0 identically. So we obtain Vt is equal uv plus u minus E of u. This plus lambda. And now replace v by lambda w. Substitute v is equal to lambda w. What happens? Substitute and then divide by lambda. Wt is equal to the bracket of uw plus 1 over lambda u minus 1 over 2e u. The bracket of u and w is equal to 1 plus 1 over 2 lambda e of delta u. And then when s lambda tends to infinity, this equation this system gets acquires the form of this Lax representation. So this Lax representation is a limit case of one of these constructions. It turns out. Now let me discuss the general picture. Let me consider one of these Lax representations that are of the following form.
And it seems this bracket is it correct? Like u of y minus u9 yeah? What working?
Max, I can send you the paper, the preprint. Okay, but you are welcome to. Well, let's take this Lax representation. I'll show that it it admits a number of generalizations. Lambda means туда все. Well, and this Lax representation has the following natural formulation in terms of the divergence-free vector fields on R2 or Hamiltonian fields. Лямбда только да, yes. So, but well, plus minus this equation minus. Okay, consider the Lie algebra as diff of R2, or not R2, but some open domain in R2. It is generated by vector fields of the following form. Oh, sorry. F Smith function, or it is isomorphic to the Lie algebra of functions of just smooth functions factorized by constants, the Poisson algebra. Well, then what we say, this Lie algebra has only one outer derivation.
Only one what?
Only one outer derivation. Let it be. Okay. The first adjoint cohomology group is one-dimensional, and it is generated by derivation. Let it be denoted by E tilde. This E tilde acts on a smooth function in the following way: f minus 1 over 2x fx minus 1 over y fy.
Сам. Царь технологии посчитаны.
Yeah. Well, perhaps some Japanese mathematician found it before, but I don't know. Okay. Well, so now what we say, we can rewrite it. Rewrite our Lux representation in the form.
Not a derivation. This is not a derivation. It's an operator of first order.
This is an operator of the first order, but it is a derivation in this Lie algebra. Operator of the first order, but well, it acts on functions, and the result is functions. It's a function. Actually, this operator corresponds to the extension of Hamiltonian vector fields to contact vector fields. Well, in terms of this operator, we rewrite our Lux representation in the following way. Once again, this algebra derivation. So actually, we can say that we consider the loop algebra functions from R to this Hamiltonian vector fields. Yes. Well, in the case when the dimension is 2, Hamiltonian vector fields and divergence-free vector fields are the same. Well, and this picture admits a number of natural generalizations. Namely, let me discuss them. Well, how many minutes?
How much time I have?
How much time I have? Well, the first generalization, we replace R by R2. And consider the following equation. Now the functions depend on t and z. This R2 with coordinates t and z. And consider the following equation. This system is called either the reduced magnetohydrodynamics equations or the Kadamtsev-Pogutsa equations. It describes the major features of the plasma dynamics in tokamaks. Whatever this feature are. Well, this equation admits a Lax representation. Let me read it, write it there. Lax representation. Well, Q of T is equal to U Q plus delta V, this V, plus lambda of E tilde of U, QZ is equal to Q plus delta U plus lambda E tilde V. E tilde is the same, is the derivation of this Lie algebra, and the only outer derivation of this Lie algebra. Lambda is the non-removable parameter. Again, there is a...
It also rises by lifting.
Yes, it appears by a lift of some symmetry of the Kadamtsev-Pogutsa equations. Не. Keylor. Okay, now, in this situation, if we replace dependence of Z, if we put that all the functions are independent of Z, we obtain the two-dimensional ideal magnetohydrodynamics equation. Ideal magnetohydrodynamics equations. If we replace this, well, this equation was considered by Zeitung. Well, we obtain this, if we remove this, we obtain the Lax representation for the two-dimensional ideal magnetohydrodynamics with the non-removable parameter. Well, now more or less evident question is, what about three-dimensional ideal magnetohydrodynamics? Well, the answer is the following. It admits a Lax representation, but without a parameter. Correctly, I don't know the parameter in this situation. So, 3D ideal magnetohydrodynamics. This equation, well, for example, it can be found in Landau-Lifshitz, volume 8, section 60. You are a specialist on this Landau and Lifshitz, and so actually, well, to obtain this equation, the equation for ideal, one must put rho, the density equal to constant in this equation. Well, let me write. The equation is the following form: curl V T is equal to minus V curl V plus B curl B. Then BT is equal to minus VB, and divergence of both V and B is identical equal to 0. This system. Commutator now V
No, I'm speaking about last one.
V.
Equal what?
Ой, sorry, I'm off this. Now we are on. We are living on another Lie algebra. Now we are in this situation, R3. The bracket is just the bracket of vector fields on R3. Not
Это все трехкомпонентно.
все трехкомпонентное.
И 4, 1 плюс 3, да?
1 плюс 3, да. Bliss system. Well, and the result is the following. This system admits the Lax representation of the form S T is equal to minus Vs plus curl B. The commutator of B and S is equal to curl B. S again is from Pauli algebra. So it's function of T and S maps T to vector to divergence free vector fields on R3. Well, and so on. Shall I write some more examples or?
Well, if they are so here without
No parameter, I don't know. Perhaps there are some parameters, but well, I don't know them. Perhaps there are some other Lax representations, but well, the only one that just by generalization of the two-dimensional situation. But in two-dimensional situations, there were lambda, but now no lambda here. Well, there are some other examples in 1, 2, 3, 4. But these are automatically because of curls. Because of curls, we can just erase them. So there are a number of other examples in dynamical meteorology, climate modeling, ocean physics, and so on. But well, let me stop because.
Okay, thank you. Thanks a lot. Questions and remarks? No question? Okay, then thank you for visiting our seminar, and we meet in a week at the same time in Zoom. Goodbye.